Alright guys, let's start going over some gauge fixing. We're starting to get into some more of the advanced stuff, right? So we're going to cover gauge fixing, we're going to cover ghost terms in QCD, we're going to take a look at a lot of terms that you're not really introduced to when learning about quantum field theory or quantum mechanics or anything about the nucleus of the atom. And to be clear here, I haven't really mentioned in this playlist yet is that we're talking about the strong force, right? The strong force is known to be this thing that sort of glues things, that sort of glues the neutron, the inside particles in the atom, right? You have an atom, right? You have this thing, right? Go to my drawing. I'll go to my drawing here, and we have this thing that is an atom, right? So we have the atom, which is, come on. We have this thing, there we go, this atom, and inside the atom we have this nucleus, and in the nucleus we have protons and neutrons, and surrounding that we have electrons, right? So these are electrons, and the inside here are protons and neutrons, right? And the strong force that sort of keeps them all glued together inside the nucleus is, so we have the strong force. That strong force is the dynamics of all of this is governed by QCD, right? So we are dealing with fundamental particles inside protons and neutrons, right? And those are going to be the quarks, right? So you have the protons. To be more specific here, you have the protons and the neutrons. Those are considered like the hadrons, and then inside of those you have even more fundamental particles, which are the quarks. You have up-down quarks, charm-strange quarks, and top-bottom quarks, right? So there's 6 of them. And so the dynamics at play that is within that domain of physics is governed by quantum chromodynamics. Okay, in this video we're going to be covering gauge fixing terms, right? So gauge fixing terms are going to be important when we start looking at how exactly do we define propagators in QCD, right? So let's go ahead and get started with this. So what is gauge fixing in QCD? Well, excuse me. We have this Lagrangian. This is our total Lagrangian so far that we sort of somewhat talked about, right? So we have this total is often written as LQCD, right? And we've talked about this term right here, right? This term here is the gluons. This term here is the gluons. This term here is the quarks. Okay, why does it keep on doing that? Gluons. This term here, maybe I'll go like this, is the quarks. And then this term here, this is going to be the gauge fixing term. We're going to talk about this today. This term here are ghost terms. They're called Fadiv, or it comes from this idea of this idea called the Fadiv-Popov ghosts. GH ghosts, right? So we're not going to talk about these quite yet, but they're important in maintaining something that we'll call a different type of symmetry that sort of extends beyond the gauge symmetry. But we're going to save this till Halloween because, I'm a little bit whimsical in that way. Anyways, and Halloween's not too far down the road because we're going to take some time to talk about gauge terms. And then in the next video, we're going to take some time to sort of review what we've covered, but also talk about source terms in QCD, right? So there's that. So between gauge fixing terms and Halloween, we're going to be talking about some source terms, source terms in QCD. Okay. Also, make sure to hit up this QR code right here if you feel so inclined to do that. Again, it's not necessary, right? Yeah, I'm still gonna be making videos even if you don't. So, okay. So one of the things that I've been doing in this playlist has been drawing analogies to gauge field theories, which is fundamentally what we're talking about here in QCD, and economic systems, right? And so if you're someone into economics, or if you're someone into politics, or how economic systems sort of what their dynamics is, gauge field theory is actually a very unique and interesting way to go about it. And so what we're going to do here is we're going to draw in and out. We're going to state what the economic analogy is to gauge fixing, and then then we'll talk about the physics and the math. So in our economic model, we noticed that to compare the durability of a widget between two factories, we needed to also consider how the durability was measured, right? So when we have a widget and it's going from one factory and to the next, we have the sort of this raw change in durability of the widget, but we also needed to take into account the protocol adjustments that we had to make in order for the durability here in this factory to be directly comparable to the durability in the other factory, because otherwise you're sort of comparing apples to oranges. So so we have this idea that, going a little bit broader, we want to talk about the value of something, right? Because in economic models, we're talking about value of things, not strictly durability. When we're talking about the value of things, there's going to be multiple, if not an infinite number of ways to measure something's value. Okay, there might not be an infinite number of ways to measure something's durability, but this is sort of a tangible model that we've used so far to understand how gauge field theory can help us in understanding economic systems. Okay, and now we're talking about gauge fixing terms, and let's now dive into this a little bit deeper. So in an economic system, the durability of some object is only one way to assess the value of some widget. So if we're abstracting this higher, we're understanding things in terms of value. Okay, so my value, your value, the value of, I don't know, some commodity. Say you're buying a car, you want to know what the value of the car is. Say you are hiring a worker to, I don't know, mow your lawn or something like that. Or sell something in your company. There is all of these have value, but the way we measure the value is something of an arbitrary thing. Okay, and there are many different factors that go in to the measuring the value of something, right? So this widget has some value, and we can measure the value in terms of its fungibility. We can measure the value in terms of its utility. How the utility, meaning like how broadly applicable is this thing, its durability, which is something we've talked about, its scarcity, its portability, its producibility, how easy is it to produce, its verifiability, how easy it is to verify some aspects about this object that we're attributing value to, and its divisibility, how easy is it to make more and more of it. If it's really hard to make more and more of it, then its value might be really high. I was recently somewhere where paintings, really nice paintings, were being sold, and it's really hard to, I could see how it would be really hard to make paintings or just to replicate a painting that's really big. These paintings are really big. They're really intricate. Right, so the value of that painting is very high because of this divisibility factor. Probably it's very hard to remake that painting exactly for what it looks like, right? So there's that, right? So all of these factors, and you could list a huge list of things that contribute to the overall value of some object. But here's the thing now, right? So for some of these things, and this is just an example, the durability of a widget we can say there's some durability that contributes to the value of the widget. It's scarcity, how much of the widget is out there already. It's producibility, how easy is it to make. Some of these things are going to share some common source, right? So the durability of the value, well, that's going to depend on what the item or what the widget is made of, right? So suppose it's made of iron. The scarcity, well, that's also going to depend on how much iron supply there is as well. And the producibility, how easy is it to produce? Well, again, that also depends on the iron supply as well. So we have this overcounting of 3 here, right? We have 1, 2, 3. Iron supply is accounting for 3 parts or 3 components of the value in this widget, and we don't want to overcount that. Okay, so we don't want to do this overcounting, because the idea here is that in order to assess the value of the thing, we need to understand all of the things that go into producing the value for that thing, but we don't want to overcount iron supply 3 times. Okay, and that's roughly what gauge fixing is going to do. It's going to help us prevent overcounting in some sense, okay? But now let's start diving a little bit more into the physics and see how and why this actually might occur like this. So, because the value can be determined in an infinite number of ways, we need to somehow fix for this infinity that we're running into, right? So this is an infinity problem, okay? This is where gauge fixing comes to play. There's no standard, widely accepted analogy for gauge fixing in economic systems for this idea of gauge fixing in economic systems, as it's a specific mathematical procedure in physics. But there's, however, a conceptual analogy, which is what we just made, can be built around the idea of standardizing measurements as well to prevent overcounting, right? So one of the ways I like to view this also is to say, we have, this is a gauge or something that you use to measure, right? And say you're measuring something. So you have a ruler, a really good example. Say I'm measuring this pen, and this pen is, 12 inches, or what's that, maybe 6 inches. And but it's also some number of centimeters, convert inches to centimeters, or it's also some millimeters, or it's also in units of, I can measure it in units of the size of these Post-it notes, right? It's about 2 Post-it notes, or it's about, if I were to take my headphone case here, it's about 1, 2, 3, 4 of my headphone cases. Or I can measure it in terms of, my external hard drive, right? The point here that I'm trying to make is that there's an infinite number of ways to measure this thing. And because gauges, or gauge field theory, is this thing that helps us measure stuff, which is sort of what we talked about already, we need to greatly truncate this, the way we measure this, so that we can actually make tangible measurements in physics, right? So the way we are going to do this is to say, let's choose one gauge, right? Let's choose, in an economic system, we choose one standard, right? The US dollar, for example, is the one standard. We're fixing the gauge. We're fixing the way we measure things here, okay? That's what it means to gauge fix. So we're fixing the way we measure this. We're measuring this in inches, and that's it, okay? That's what gauge fixing is going to do, okay? So another good economic model, I think, that helps here is to imagine an international economic system where every company's value is reported in multiple currencies simultaneously. So we can measure the value of a company in US dollars, in euros, Japanese yen, whatever. if you decide to calculate the total value of all assets in the system, you'd face a fundamental infinity problem. You're adding all of this together, okay? And you just get to infinity. So a single asset, i.e. a factory, has an infinite number of mathematical descriptions, one for each currency and exchange rate. So summing all of these descriptions would lead to a widely inflated and meaningless total as you're counting the same physical asset repeatedly. And this is analogous to the redundant degrees of freedom in the path integral formulation for QCD, which is what we'll come to across later. But there's this idea of this redundant degrees of freedom in QCD that we need to get rid of. And most importantly, that's going to help us define a propagator. Okay, we'll get there. But this fundamentally, this makes the integral of our action diverge. So we don't want this divergence to happen. All right, so now let's go ahead and start getting into, or I actually have this here, and then we'll start getting into some more of the physics. Gauge fixing is analogous to an international agreement to a single standardized currency and accounting methods for all economic systems. By imposing a rule like all assets must be in US dollars, you're fixing the gauge, okay? This rule eliminates the redundancy by selecting only one unique value for each asset. It ensures that when you sum all the values, you get a finite and physically meaningful total that accurately reflects real-world assets. All right. The gauge fixing term in the Lagrangian is the mathematical representation of this rule. All right. Now let's start getting into the physics. So in QCD, gauge fixing is going to fix a propagator. Okay. Now let's take a look at this diagram that I've made. We've talked about this right here, right? So this here, this is our gluon part. This is our quark part, right? So our gluons and our quarks. Then we have this gauge fixing term that we'll talk about in a few seconds. And we have our ghosts. But what the ghosts are going to do, I'll kind of introduce them here. But what the ghosts are going to do is we're going to have this thing we said was gauge symmetric. We've seen how this is gauge symmetric, right? When you add that arbitrary term, right, that arbitrary lambda term we talked about, we saw that had no effect on the physics at play here. Right? So this was gauge symmetric in that respect. These are our gauge functions. Not gauge symmetric, right? So when we add the gauge fixing term, we're going to see that we break that symmetry, right? So because now we have this A here, we need to incorporate this into the A, but because of this term, there is no, I'll erase some of this, that we break that gauge symmetry, right? So, okay, that's a problem. And so to fix that problem, we introduce our ghosts. And ghosts are these non-physical fields that are going to help us in regaining the symmetry. But that symmetry that we regain it's not gauge symmetry per se, because the gauge symmetry came from here. So this is not really gauge symmetric, right? This is what's gauge symmetric. Adding this breaks the gauge symmetry. Adding this regains symmetry, but it's not. It's something broader than gauge symmetry. It's something that we're going to call BRST symmetry, and these are the first. These are the first letters in the names of people. We'll see that later when we start talking about ghosts. So keep with me until Halloween at least to do that. So when we develop a propagator, let's recall just in quantum field theory, if you've been staying up to date on that playlist, we need to have a term in the Lagrangian that's squared in the derivative, and this will give us sort of a well-behaved propagator. We talked about what it meant to be a well-behaved propagator. If not, you can go to that video. I'll link it here in this video if you're interested in looking at that. And I try to go through that as self-explanatory as possible. But the idea here is that we need this squared derivative term, okay? We need the squared derivative term to define a propagator so that we can write our Lagrangian or our action in this way, okay? And that's what it means when we were talking about the action not diverging. That's what this was, and we're going to see that once we gauge fix, we get current, we get quark current, and we get a self-interacting current as well. We'll take a look at that probably in the next video on QCD. But the idea here is that we will say that a well-behaved propagator is one that has an inverse, right? So if we say that this is the inverse to some propagator, that propagator is the Feynman propagator, okay? And the Feynman propagator for scalar fields looks like this, for spinor fields looks like this, and for vector fields looks like this. And because gluons are described as vectors, we are going to see, we're going to use this term, we're going to take a look at this term right here, okay? So let's go ahead and do that. So our squared derivative term is our gauge fixing term. That's this thing right here, okay? And we have this chi right here. That's important, but let's ignore that really quick. So here is our, I'll make my pointer a little bit bigger here. Here's our the numerator in our propagator, right? So if we go back to the propagator really quick, we have, I'll just erase this, we have the metric, right, and our momenta, okay? And here's our metric and our momenta, and then we have this squared term. We don't really, this is something of a normalizing term, but let's just go back here really quick one more time. We have the metric, right? This is somewhat, it's a little bit arbitrary as to why we're putting that square term right there, and it doesn't really matter for the sake of what we're talking about right now. But let's just take a look here. The form is somewhat similar though, right? We have the m squared. It can almost sort of it can be thought of as multiplying both sides by m squared, okay? So, and because mass is when we're talking about special relativity, we're talking about mass as being integrally related to momentum. We're taking the time component there, and so this is all to say that this comes from that mass term, okay? So we have the metric part, and we have our two momenta part, right? So the G mu nu term is just the metric tensor, and by adding the gauge fixing term, it is not too difficult to see we now just add this bit right here, right? So originally the vector Feynman propagator term, this is what that is, right? So that's this guy right here, right? And again, this k squared term comes from just multiplying both sides by m squared, or this by m squared and this by m squared, right? We're ignoring the denominator right now. We can effectively ignore the denominator because when we calculate these propagators, you'll see, you can go to my video on QFT, when we calculate these propagators, these denominators are sort of given to us already, irregardless of what our actual Lagrangian looks like, okay? And so we have this term, so that's that term that we see in the propagator, and then this is the gauge fixed term, okay? So we're adding we're adding this bit right here, right? So this bit here, when we do the Euler-Lagrange equations onto this bit, we get the momentum squared, okay? We're going to get this term, and we get this then, right? So, right, because this, k mu, k nu, k mu, k nu, and then so we can effectively just take this out here. And so this is I'll get my pen here. Right, so we have this term right here. Okay. So this chi thing is what we want to focus on here, but let's just go ahead a little bit more and see. Yeah. So that chi term, right? So okay. Yeah. Okay. So that chi term, right? That is part of a family of terms, right? So this is actually quite interesting. When I started learning about this, this I thought was quite illuminating. Depending on how we choose the values of chi, we can fix the gauge in a certain way. Okay, and this is just a number, right? There's some names to different values of chi that's known in the literature. So when chi is 0, right? So our term we had was 1 over chi minus 1 times our k mu k nu term, right? So when chi goes to 0, we just have the k mu k nu part, right? So that's for this guy here. This gauge is obtained by taking the limit as chi approaches 0. It's often used in non-perturbative calculations, such as those in lattice QCD, because it simplifies certain aspects of the theory in the long-distance non-perturbative regime. Okay. So not in the long distance, right? So as chi goes to 0, we're getting closer and closer. We're becoming more local. Okay. So, and then we have when chi equals 1, this is the Feynman T. Hooft gauge. T. Hooft he's a famous theoretical physicist. And this gauge, the main advantage is that it significantly simplifies the gluon propagator, right? Because imagine if this was 1, right, that'd be 1 minus 1, this whole thing would go to 0. Okay, so we have that going for us for the Feynman T. Hooft gauge. And this is a key component in calculating Feynman diagrams. In this gauge, the gluon propagator takes a very clean, simple form, making the perturbative calculations much more straightforward. Again, because that latter term goes to 0. Then we have this thing called the Yenny gauge. This is something I hadn't heard about, and when I did, I thought kind of a funny name, but also very, very interesting. The Yenny gauge is less common, but known for its ability to simplify certain infrared divergences in calculations, particularly in quantum electrodynamics, and it was used by physicist Donald R. Yenny for this purpose. So this is the Yenny gauge. And then we have the unitary gauge, and this represents a specific limit of the R chi gauge, right? That's chi right here, where the gauge fixing parameter diverges, leading to the unitary gauge, which is particularly useful for its simplicity in eliminating unphysical degrees of freedom. Okay, so we could just think about this really quick. When we have 1 over something that tends to infinity minus 1, right, this bit is going to go to 0, okay, and so we're going to get minus k mu k nu, okay. All right. Oh, and I think, when I talked about the Landau gauge, that was 0. This tends to 0, so this actually gets bigger, right? So something bigger minus 1, so we're actually going to get some number, right? Some large number in front of here for the Landau gauge, right? So this is like, so this is going to give us some number. We'll just say A times k mu k nu, and then the unitary gauge is going to give us, right, that term is going to be 0 because the denominator gets larger and larger. Okay, so that is the unitary gauge. Let's do a little bit more physics here. The caveat to adding this gauge term, however, is that we break gauge symmetry, right? So to ensure that the physical results remain unchanged, a compensatory term known as Faddeev Popov ghosts or ghost determinants must also be included. The reason I say determinant is that because these things are ultimately matrices, right? These things are not this, but we have a matrix valued gauge field. So the determinant of the matrix is going to be important in helping us understand the action principle for QCD. We haven't touched actions yet. We're going to, but that's one of the reasons that's one of the ways we get rid of this divergence when we add the ghost terms, which ultimately lead to adding that determinant as well. But we'll talk about that in later videos. And so this determinant can be represented as an integral over a set of unphysical fields called Fediev-Popov ghost fields. Right, so we have the Fediev-Popov determinant, we have the Fediev-Popov ghosts, and these are those fields, these C fields. And they're unphysical fields, which is why they're called ghosts. Ghosts are unphysical things if you don't believe in them, whatever. But that's why they're called ghost terms. So before we get into these ghost terms, this is where the naming gets very strict, because physicists have decided to say that gauge symmetry only applies to the gauge fields. When we have the ghost fields involved, then we have something called this new symmetry called BRST symmetry. We're not going to talk about that anymore in this video. The rest of this video, we're going to do a little bit of physics derivations and then call it good. And so the look at me, I'm dwelling on BRST now a little bit, but we can do this. So the BRST symmetry is a quantum symmetry that emerges specifically to address problems caused by gauge symmetry. It's a new hidden symmetry that acts on the entire gauge field Lagrangian, which includes the original gluon fields, the gauge fixing terms, and the ghost fields. And the ghost fields are added to maintain the symmetry if we look at our Lagrangian again. Right, so here's the ghost term. Again, I'm not calling this gauge symmetric. We're calling that BRST symmetric. But now let's take a look at what happens when we now take into account the gauge fields, or the gauge fixing. When we look at so here's our Lagrangian. We're going to ignore the quark terms for right now, okay? Because the quark terms don't have this, they don't have this a mu part in there. They do have the derivative, like the covariant derivative of a mu, or they do have the covariant derivative involved, in which there is an a mu. But let's just take a look at how this term affects just the gluon part, not the quarks. Right, so why is that not? There we go. So when we apply the Euler-Lagrange equations, we can see, I'll get my pointer out here, make my pointer bigger. We can see here that we have, so we start here. When we apply the Euler-Lagrange equations here, well, there is going to be no a alone here, right? There's no derivative of a in, there's no a here alone in the ghost term, but there is a derivative of a in the ghost term, which is just what the ghost term is. And so when we do that, right, we get this term here, okay, and then you can pause the screen if you want, but I'm just going through the math, the calculus steps here. To get from here to here, then we have this, we have our constant. This is this squared, right? So we bring the 2 out and we do this, and then we're going to require some Kronecker deltas, right? So to get from here to here, we're just taking this step right here, right? So we're defining some Kronecker deltas. We add we get the metric from those, and then so we get this term right here. So then when we take the derivative, right, because this here comes from Euler-Lagrange equations. So when we take the derivative of this, that's taking the derivative of all this right here. And then from here, we're just continuing with that derivative, and we get this, where this here, I will take my pen out again. This here is the D'Alembert of the system here, right? So actually, yes, yeah, that's good, right? So effectively, what has happened to our equations of motion is that we now add this term, right? So this term here comes from adding our gauge fixing term, right? So let's do that, right? So thus the resulting equations of motion are going to be this right here, okay? Where we have this came from our, again, this is just for the gluons, right? Again, just for the gluons. Just for the gluons. And so we had this term right here, right? So and then we have the source term, right? So this source term, it can be 0, right? If that's 0, then this is going to be equal to the negative of this. But this then is going to be, I'll just erase these guys really quick. And then I'll just get my pointer out again. So we get this here, all right? And then, so the J terms, this is the color current, and is 0 for the non-homogeneous case. In other words, if there's no mixing between spin and color. And this is to say that if the color current is 0, then the gauge fixing term results in this, right? We can multiply both sides by chi, and we get this. So the derivative in our, these are our field strength tensor. This is our field strength tensor, and this here is our the result that we get from fixing the gauge. So our field strength tensor, when scaled, and when taking a derivative and scaled, is directly related to how we gauge fix our fields. Okay. And so later we're going to see that Faddeev-Popov ghosts do not directly restore gauge invariance to the classical Euler-Lagrange equations of motion, which remain gauge fixed. Instead, they're going to ensure that the quantum theory's physical observables, like the S matrix for scattering amplitudes, are independent of the arbitrary gauge parameter chi, right? So this chi is not going to depend, or it's not going to do anything to when we add the ghost terms, okay? Thus preventing the fundamental gauge invariance of the overall quantum result, okay? And that's what I've got for you in this video, right? So we've talked about gauge fixing terms, how that influences the dynamics, and we're going to see then in the next video we're going to take a look at what these guys look like, right? That's a very thick pen. We're going to investigate these guys, okay? And so that's what I got for you guys, right? So make sure to hit that like and subscribe button. Make sure to hit me up on the QR code if you want to do that. But with that being said, I will see you guys in the next video.